exercises that I can present here parts of my work. This work is first a short warning. It's more in the setting of PDEs, but I think the ideas there can be very interesting for calculus of variations as well. And the work here is done together with my PhD supervisor, Malte Peter, and with Markus Gahn and Soren Popp. So let me give you first a short motivation. So what we can see here is a tree. So it's a close-up view of the inside of a tree, and there we have some pipes, and in these pipes some fluid or tree sap can flow, but due to some bacteria infection of the tree, the bacteria can produce biofilm, and then some clogging inside these pipes can occur. And what we want to do is we want to derive some effective model by with homogenization techniques for this application. Okay, so the outline of my talk is first I want to give, present an abstract framework for the homogenization in this evolving porous media. Then we will apply it to the homogenization of decoupled Stokes flow. Decoupled means here that we have some domain evolution given, and then in the next part we consider a reaction-diffusion process which is coupled with the domain evolution. Then we will do the homogenization, and then in the end we take a look on our current work where we want to combine these two processes in one process. Okay. So let me first do a short recap about the homogenization and two-scale conversions. We have here a classical elliptical problem where we have a heterogeneous coefficient, and we scale this coefficient by epsilon and let epsilon tend to 0 in order to derive some effective model. Okay, so this should be everything well known, but here we can now also have the heterogeneity by the domain itself and not by a coefficient. So now we define the problem on the domain omega epsilon, which is somehow here only the white region. And this is also easy if the domain here is strictly periodic, but in our setting we have an evolving domain. And this domain evolution can, for example, look like this. And at every point in time the domain looks differently, and in particular we cannot assume that the domain is strictly periodic during the whole process. And then the homogenization becomes more complicated. And if we compare now with this classical homogenization problem where we know how we can do the homogenization, the difficulty arises already in the stationary case when we have the non-periodicity. So in fact, not only the domain evolution of the problem, but also the non-periodicity of the domain. In our approach, we want to transform this problem from this non-periodic domain to a periodic domain, but thereby we get here some coefficient, and by controlling these coefficients we can somehow do the homogenization for this transformed problem. Okay. So in order to explain a little bit more in detail how we do this, let's first take a look on the two-scale convergence and how we do the homogenization of two-scale convergence. So if we want to pass to a limit for this left-hand side of the weak formulation, the problem is that we have only here some weak convergence for the coefficient in general, and by compactness argument we have only weak convergence for the gradient, and then we cannot pass to the limit. And what we want to have is some strong convergence, but in reality we have no strong convergence for this coefficient. The solution is somehow, or one solution is given by two-scale convergence, which somehow improves this weak convergence to weak two-scale convergence, which is a little bit stronger, and we can decrease this convergence to strong two-scale convergence, and then we have here some strong two-scale convergence for this coefficient, and then we can pass somehow in the two-scale sense to the limit. Okay, so So what is two-scale convergence? Two-scale convergence is we have the sequence u epsilon and L2 omega, and our limit function depends now on additional y variable, and this type of weak convergence can capture by suitable chosen test function also the microscopic oscillation on the epsilon scale. Yeah, so you can see here these test functions depend on the microscopic and microscopic variable, and here the limit function depends also on a microscopic variable. So for this notion of two-scale convergence, we have also some strong two-scale convergence, which is motivated by strictly convex Banach spaces. If we have additionally the convergence of the norm, we have the strong convergence. So we cannot formulate this two-scale convergence in a classical sense of having the convergence inside a norm, because our limit function here is in a different phase than the sequence itself. Okay, so but this two-scale convergence is quite nice. So we have good properties, and first we can see it's somehow in between the classical weak convergence in LP spaces and the strong convergence in LP spaces. And here in between is the two-scale convergence. You can think like this, but we have also some multiplication. So if we define the two-scale convergence here for general LP spaces instead of only L2, we have also this product rule somehow, and change between the product and the limit in the process. And then what is very important is some weak compactness results. So if the sequence is bounded in L2, we can test in subsequence and get the existence of a two-scale limit function. And now the critical point is if we have also a bound for the gradients itself, then we can pass also to subsequence to get the gradients not only converge to the x gradient of the function u0 of x, like in the classical weak compactness results for Sobolev spaces, but we get additionally some correction, which is in y gradient of some corrector u1. And this additional information will allow to do basically the homogenization. Okay, but before we come to the evolving domain setting, we take a short look on how the homogenization is done in general. So if we have our weak formulation, then we can derive easily some a priori estimates, get the compactness results, and then we choose some suitable test functions here, and then we test this equation here, can test to the limit, and get some two-scale limit problem. So this limit problem will become important later. And yeah, this limit problem lives in the domain omega times y, so also on a microscopic variable. And then we can, but we have also this additional u1, and we can show that u1 depends linearly on u0, and then we can eliminate u1, and then we get this effective limit problem here, where this effective coefficient a hom depends now on, or is given by solutions of so-called cell problems. Okay, what's important here is that, and this is what we will use later on, is that it is enough that we have here some strong two-scale convergence for this coefficient in order to pass here to the limit. And if it's some general strong two-scale convergence, this limit here can also depend on x, and thereby the cell problems can depend on x as well, and then this effective coefficient can depend on x too. Okay. You can do the same argument if you are in the setting of a perforated domain, and there you have to be slightly careful with the compactness results, and often you need also some control of the interface terms. So here we have with omega epsilon a lot of interface terms inside the domain. But you can do this if you are in the case of strictly periodicity. But now, in our case, where we have no strict periodicity of the domain, it's not so simple. And there, Malte Peter has proposed the following approach, that we simply transform this micro problem on this evolving non-periodic domain on a periodic substitute domain, and then we do the homogenization for this problem, which is on the periodic domain and should be a little bit easier. And then we transform the problem back. So to do a little bit more of pictures, so we have here the non-periodic domain transformed on the periodic domain. Thereby the non-periodicity of the domain becomes a non-periodicity of the equations. So basically, not so much, but this non-periodicity of the equation can be treated more easy. And then the homogenization, and then we have the back transformation. But if we take here how we can do this, so the non-periodic domain, if we have, now let's assume for this point we have a diffeomorphism, psi epsilon from the periodic to the non-periodic domain. We transform the quantities here, and then arrive at this equation. And so we see here basically that we have to control the two-scale convergence of this additional term here in order to pass to the limit. And if this can be controlled, then the homogenization can be done. And in this setting, also for some reaction diffusion problem, this has been done, or also for elasticity problems. But all these works has been done in the sense that only the homogenization here had been done. And we still see here, for example, this question mark, so it was not clear that this actually commutes, so that this approach gives the homogenization of the actual problem. And there's a second issue, it's this back transformation does not already gives transformation independent limit problem, so it's no complete back transformation. So we are on the actually evolving two-scale domain, but there are still some transformation included, and they are in the effective problem and the cell problems. And it's not clear how they can cancel out. But if we think back at the homogenization, we have seen that in between here, we have this two-scale limit problem, which we got by applying the two-scale convergence. And then we had splitted the y variable. What we can do now is we can transform this problem back. We can show that this left-hand side actually commutes. The advantage hereby is that this evolving two-scale limit problem is now transformation independent. And then we can split here the y variable and arrive at the transformation independent limit problem. And it can be shown by passing somehow this way that these two problems are equivalent. And yeah, so this is the approach which we want to use. And the critical point here are these transformation rules. And for the sequence u epsilon, and after transforming this u epsilon, we get that the two-scale convergence is equivalent to the two-scale convergence of the transformed quantities. Where we transform the limit by somehow psi 0 is the two-scale limit of psi epsilon. And now the critical point is that in applying two-scale convergence, that we always have some compactness result like this, where we have this additional y gradient, this corrector. And this two-scale convergence can actually also be transformed in the fixed domain. But the critical point is that we cannot apply the same transformation rule here for the corrector, but we have to correct this corrector additionally by this term. And if we have this, we can do get everything without get rid of all the transformations by the back transformation. Okay. Now we want to apply this for the homogenization of the Stokes field. So we consider the stationary Stokes equation on an evolving domain at first. And now we assume that we are in this previous setting by having these diffeomorphisms. And in this Stokes equation we have at the interface, which is here the orange term, you have that the velocity of the fluid is equal to the velocity of the interface. And since we have this incompressibility condition, we have somehow to ensure that the fluid can flow out or in at the outer boundary, otherwise this evolving domain would somehow violate this incompressibility. We allow this by having this normal stress boundary condition at the outer boundary. Okay, so how we do the homogenization for this? We first substitute these Dirichlet boundary values and this interface velocity. This can be described in terms of psi epsilon, which is here. Then we get this weak formulation, and in the next step we transform this weak formulation, this psi epsilon, and by this transformation we get also these Jacobian terms, which we have seen a few slides before. And the important point here is that this symmetric gradient, or the transformation of the symmetric gradient, gives us this additional matrix term, matrices inside this symmetric gradient. And now this complicates somehow the homogenization because we have to derive the a priori estimates. So we need these classical a priori estimates for the homogenization. The second difficulty arises because of this inhomogeneous divergence condition here. But we could show the existence in these a priori estimates by deriving some Korn inequality for the two-scale transformations, where we have control somehow this transformed symmetric gradient independently of epsilon, and somehow these transformations, if they have somehow good properties. And we also derived some divergence operator, an inverse divergence operator, and with suitable epsilon scaling here. And then we could control these, or could derive these a priori estimates, and could do the homogenization and of the transform problem, transform it back, and arrive at the end at this limit result. So for the fluid velocity and the pressure, we can extend the fluid velocity by 0 on the into the solid part, and then we get some weak convergence, and the pressure will be extended by taking the mean value in every cell, or epsilon scale cell. We get the strong convergence, and V and P are the solution of the following Darcy's law for evolving microstructure, which is given here. It looks like the classical Darcy's law. So the velocity is equal to the negative gradient of P, but now the permeability becomes time and space dependent because it has somehow to capture the local microstructure. And this is done by the cell problems, which are now defined on X and so space and time dependent cell reference cells. And the new interesting additional term is that we have this inhomogeneous divergence condition. So this effective fluid velocity is not divergence free, but get this additional divergence, which is somehow the time derivative of the porosity. And then this, if you combine these two equations, this time derivative of the porosity becomes the new source term for the pressure. So this is the result for the homogenization of the Stokes problem. And here it's somehow the linear theory, and because the transformation had been all given a priori. And in the next part, okay, before we come to this part, we will also consider the stationary Stokes flow and get some, where we get some Darcy's law with memory for evolving microstructure. So yeah, instead of, it looks very similar, but we get here this additional convolution type term for the fluid velocity. Okay, but now let's go to the Hubble problem. So there we want to couple the domain evolution with the process itself. So therefore we have to somehow simplify the domain evolution or the type of the domain. And we do it by assuming that we have only spherical obstacles, and the green and gray region is somehow the obstacle, and it's bounded by below with an min and by above with R max. So the idea is that we have some solid part here inside, and from an application point of view, some biofilm can attach here at the solid part, and this is the green region. And so this is the region where we have no fluid flow, is this total region, and this region can grow or shrink. And so we have in every cell such an obstacle, and these obstacles here are now time dependent. And yeah, so this is the very simple domain which we will consider, and we couple this with the process by taking now a reaction diffusion advection term of the equation here, and then we say, okay, the interface reaction rate is depends on the value u epsilon, and here also on r epsilon, and this is only in order to ensure that the obstacles cannot become too large or too small. And yeah, so this reaction rate is also here in this term, so the evolution of the radii, and it's modeled in the sense that this green region has some constant density Cs, and every concentration which we lose in the white region where the diffusion happens becomes solid green. Okay, and then we have here also the Stokes flow for in order to model the Stokes equation. And now we simplify this model at first for the homogenization, so we ignore the advective term, so we can drop the Stokes equation in the first step. We have to add this term in order to have conservation of mass. And now we consider here the homogenization of this process. And therefore we transform these equations on a strictly periodic domain, and the strictly periodic domain is given by some fixed value for this radius, which is always the same. So we construct a family of diffeomorphisms, and here we have the Jacobians of these diffeomorphisms. And the important thing here is that these diffeomorphisms depends actually on this domain omega epsilon t, and so they depend on the radii. And so all these quantities, which is stressed here, depend on the radii, and then the transformed equation, all these quantities are depending on the radii, and these radii depend on the function u epsilon itself. So thereby this equation becomes highly nonlinear. And what's interesting here is this term, this is an artificial advection term which arises by the transformation of the equations. But it is of order epsilon, so it cancels, or we can ignore it. And yeah, for this nonlinear problem, we could show some existence and uniqueness result. So we could control the solution u epsilon and the gradient of u epsilon actually also epsilon independently, which is somehow useful for the later compactness results. However, if we go back to the equation, we see that this the time derivative, the natural formulation is j epsilon u epsilon. So it's also the reason why we could only control this time derivative uniformly with respect to epsilon, and not the time derivative of u epsilon. So this would be somehow nice if we have this, because if we have this, we could control this, we could apply some classical Lyon or Bohr lemma in order to derive some strong compactness results. But this is not possible, and other approach would maybe to have some strong convergence for this term, but there's the lack of controlling this gradient. So yeah, it's not trivial to get some strong convergence. what we did is instead we applied the step-up argument and could control somehow the shift with respect to time of u epsilon uniformly with respect to epsilon, and having this uniform convergence to 0, we somehow don't need again this time derivative of u epsilon, and then we get some compactness results, so we get some solution u or some function u0 in this space in a subsequence such that we have the strong two-scale convergence. So here we have to be slightly careful because we are in the two-scale setting. We have to extend somehow this function u epsilon on the whole domain omega, for example by 0, and then we can formulate this convergence term. Okay, and having this two-scale convergence, we can derive some two-scale convergence of the, or some strong convergence of the radii, and therefore we have to interpret this radii by as a cell-wise constant function. So in every cell, we set the value r epsilon as the value of the radius in this cell, and then we could derive some strong two-scale convergence of these coefficients, and then we can pass to the limit in the transformed equation, and then transform the problem back, and in the end arrive at this limit equation. And this limit equation is now the effective problem, and we see that it is defined on a fixed domain. So we got rid of the evolving domain, and we have now an effective diffusion coefficient which depends on the radii, and the radii they are defined all pointwise in omega. So at every point in omega we have an ODE for the radii, and what's also interesting is that the time derivative is still scaled by the porosity, and yeah, so this is our limit result for the diffusion equation, reaction-diffusion equation. And now what we currently do is we want to couple this with this advective term, so basically combine everything which I have told in the previous minutes, and so thereby we have already derived some a priori estimates, but they become a little bit more complicated. In particular, the derivation of such a uniform bound for this time derivative becomes problematic, but we could solve this by deriving first these estimates, and then we could also conclude this L-infinity estimate, which allowed us then to derive this uniform bound for the time derivative. And yeah, then we made our compactness results a little bit more abstract in order to avoid to work too much with the equation itself. So we could now rely now only on some a priori estimates. So if we have these a priori estimates, we get this uniform control of the shift of the determinant. We get directly the strong convergence of u epsilon and do not have to conclude to derive this estimate by taking a look on the equations itself. So now it's somehow easier because we only have to derive the a priori estimates here. Okay, and with this we can also pass now to the homogenization limit for this advection-reaction-diffusion problem. And we have this limit result where all these quantities, so this permeability is defined as here in the Stokes problem, and this effective terms, effective diffusion equation, as in this reaction-diffusion problem. Yeah, so now let me conclude with a short outlook what we can do after this. So far we have only considered non-periodic microstructure in the sense that the cells are still periodic, but inside the cells we have no periodicity. We have transformed this problem, done the homogenization there, and transformed the problem back. Now, for example, if we want to consider some elastic material, we have maybe also some microscopic deformation because someone wants to pull here this domain, or maybe we have evolution inside the cells which is so large that it even affects the macroscopic shape of the object. And so an idea would be to extend this approach to somehow doing such an approach where we have somehow slightly modified the two-scale convergence term, because we have now here in this setting not only always the same shape of the effect of the cells, but also different cell shapes. So the result we could expect that we have two different limit transformations and not only one limit transformation, which we had so far. Okay, and so let me conclude with what we have seen. So we have seen this transformation approach, that you can use it for the homogenization in the setting of PDEs. And so maybe it's also interesting to apply in the setting of calculus of variations, these transformations. And we have seen that you can apply it successfully for the homogenization of the Stokes approach, where we have derived this Korn type inequality and obtained this Darcy's law for evolving microstructure. And we have also seen that this approach is not too restrictive, because we have somehow managed to consider also a free boundary problem in this setting. And for this we have also seen now the existence and some compactness results, and the limit problem, which was in the end very simple on a fixed domain, and so was also not on an evolving domain anymore. Yeah, and then in the end we have seen this extension to the advection-reaction-diffusion process. So with this, I would like to thank you for your attention, and I'm happy to answer questions.